I'm done. The floor is yours. Chris Berry, what's up, man?
Hey, what's up? So I disagree with Stingray's analysis. You can have what appears to be a hard horizon line on a flat surface. So we still don't know if what you showed was a hard physical horizon or not.
That didn't make any sense at all.
No.
Hey, really quick. A little mistake on Barney. He say physical, real, and apparent horizon. He meant because he put physical twice. So physical, real, and apparent horizon, and then we got the geometrical.
Well, I disagree with that too. But
So what do you disagree about?
So Stingray is trying to say because they took this picture from higher up, that this is the actual physical geometry of the Earth. Is that my understanding right?
Sorry, say that again, Chris, because I was just reading something in the chat.
So your argument by showing that image is you're saying because they took this so much higher up, this is the actual geometry of the Earth.
Well, sorry. Well, Ban is semi-correct and also not correct because I can build point cloud data and tessellate it to represent real topology of objects, Barney. But in a conceptual sense, Barney's right. I don't mean geometry, I mean physical. So what I mean is when we're looking down, obviously the physical horizon is the thing that causes blockages, but we're optically looking at it through refraction. My simple statement is that if we have observations of such magnitude that refraction effect cannot alter in part half of the smallest unit, in other words, rounding it wouldn't actually change the value of it. So let's say we were measuring something to centimeters, and that's all we could ever do. And the only difference that we could have is like a millimeter, then we wouldn't care if it's a millimeter out because it can never alter that centimeter. And I'm saying when we look from that GoPro, the physical horizon there is so unaffected by in any magnitude by the refraction that we would see, we can almost ignore it.
Yeah, but refraction. My point is, refraction is only one aspect of the apparent horizon.
But technically he wasn't using that image to prove the Earth is a globe. He was using it to illustrate the point that he's making, that when it's sub-pixel refraction, it doesn't make any difference.
Doesn't make any difference to what?
To what we see.
Using the apparent and the geometric horizon at great heights does not matter. It does not give you a significant error. And if you believe that there's an error, Chris, let's go ahead and do the math together. You want to do the math, Chris?
I don't know what you mean by error. I'm just saying that
it means that you have a different radius for measuring a geometric horizon and an apparent horizon. However, from great heights, those differences are so tiny, they are insignificant and can be safely ignored. Would you like to do the math together right now, Chris? Just show everybody how much of an error you're talking about. Let's do the math together. You want to do that?
You can do it if you want.
No, I want to do it with you because you're the one claiming that it's different. So let's have you show your work and show how much of an error it is. Would you like to do the math?
Well, you're making formula. You and Dean are making the claim, so you guys.
Do you know the formula? What's the formula, Chris?
What's the
Alberuni formula? What's the Alberuni formula? Is it height?
I don't know the Alberuni formula.
Height times cosine alpha over 1 minus cosine alpha. Okay, so let's go ahead and do it. You want to do a sample problem?
Go ahead. Go ahead.
No, you're going to do it to show everybody that you've done this work and can tell how much of an error
but have you done it, or are you just
making the
claims?
Well, no, I sure have.
So then do it and show us.
I already have on a video, but I want you
But we're talking
to
about something specific here. So Dean's got a specific example. Is that not what you're talking about?
Let's go ahead and do it. All right, so let's ask Dean what the drop to the horizon is from the ISS. Does Dean know that?
Dean absolutely does not know the drop to the horizon from the ISS.
Oh, darn. So it's a moot point to be talking about this.
No, I can tell you what the drop from 45,000 feet is. It's 3.75 degrees. Would you like to go ahead and do the math together right now?
Where are you getting that? Where did you get that from?
A direct measurement from an airplane.
From who? I'm sorry?
I have a direct measurement from an airplane.
Yeah.
What? Okay.
So how did you calculate the variance in both the drop due to the curved windows and refraction.
It's not a curved window. It's an instrument. So
the windows that you looked at out through the airplane weren't curved slightly?
No, it wasn't a visual estimation. It is a measurement from the aircraft. It tells you how far the drop to the horizon is.
How was the measurement taken then? Maybe I'm just
by the aviation instruments in the aircraft. It tells you how far the drop to the horizon is from the horizontal. So you can't get out of it.
How does the instrument know? Hold on. Just chill out, Bob.
Because that's what it's designed to do.
How does it know, though?
It's designed to do that.
But how was it designed to do that?
It directly measures and how the instrument is built is none of our concern. The fact that it's an accurate measurement
is it measuring what appears to be the physical horizon?
It's measuring the visible horizon, yes.
Right. So it's measuring the visible horizon. So there's an invisible part of the horizon that we can't see. Is that correct?
No.
It's not.
No.
So all the horizon is always visible.
From this instrument, it is, yes. That's what it's designed to do.
Well, you just said it's measuring the visible part of the horizon, so I'm just trying to figure out
Do you have a problem with the fact that this instrument specifically is designed to give an accurate drop to the horizon, which is 3.75 degrees, and I'm not going to discuss that any further. That's what it is.
It's to give a drop to the apparent horizon, correct?
Yes.
Okay, so it's only an apparent measurement then.
No, it's an actual measurement to the apparent horizon. So what's your point?
Well, it's an actual measure. Yeah,
do you agree with the fact that it is an accurate measurement?
So we don't know if that's the actual geometric horizon or not. Then,
it's not the geometric horizon. It's the apparent
horizon. So why are we using it as a physical measurement?
Because we're going to demonstrate the difference that it makes. Because you and I are going to do the math together. So here we're going to start off. We're going to get your calculator out and multiply 45,000, which is the height of the aircraft, times the cosine of 3.75 degrees. Go ahead and do it.
I quit. I don't know how to do that.
You can't you can't multiply 45,000 by the cosine of 3.75 degrees?
I haven't even pulled the calculator. I'm just thinking about doing it.
It sounds like you're about to reify your model to me. Is what it sounds.
No,
like.
Chris
he still wants to ask about the curved window.
There's no window involved. Are you doing the math, Chris?
No, he's not.
I'm reading comments, to be honest.
Okay.
Yeah,
so
he's not going to do it.
Because
you
the
can't
point
do the math.
you said you're measuring to an apparent horizon is the point I stopped caring.
I understand that you can't do the math, but I'll be happy to walk you through it if you would like, so you can see how much of an error the apparent horizon makes compared to the actual geometric horizon. But you don't want to do that, do you? Because you know that it's going to come out to be next to nothing.
Okay, use the black swan then. Why don't you do that?
You can't use the black. You can't do an Alberuni measurement from sea level. Why do you think not? Why do you think not?
Well, because the horizon's always and only ever apparent.
No.
No matter the height, the horizon's always apparent.
No, if you multiply, the formula is height times cosine of the drop to the horizon.
Why are you using a reified formula? We're talking about what the horizon is.
It's not a reified formula.
Yes, it is. How are you measuring to an apparent position?
You take a picture of it and look at it.
Yeah, that's it.
So what's the drop to what's the elevation of the black swan and what is the drop to the horizon? We'll go ahead and do it. Of course you can't because the height is essentially 0 and
it's 3 feet. It's not 0. It's 3 feet. And the horizon is like 10.5 miles away or something like that.
What was the formula again, Bob? It was 45,000 times cosine.
It's height times the cosine of the angle, the dip angle.
What are the values we're using?
Over 1 minus the cosine of the dip angle.
Where are you getting the dip angle from?
It's measured right off the instrument. So the height is 45,000 feet.
Right. So you're putting into the calculation an apparent position.
The dip angle is 3.75 degrees. Measured.
That's an apparent dip angle then.
It's a measured dip angle.
It's apparent because the position that you measured.
But it's still a measured dip angle. Okay. You understand that it's a measured dip angle, right?
Would you argue that the black swan is an apparent position and measurement?
I'm not going to argue the black swan at all.
Yeah,
I've
you
already
would,
explained
wouldn't you? You would have to. You would say, oh, well, the black swan is only apparent. It's not, the horizon isn't really 2.5 miles away.
Yeah,
Bob and Chris, really quick. The boss queen in the chat say, move on.
All right.
Shout out to Wait.
But in any event, for Brenda, who actually wants to do the math on this, the angle's 3.75 degrees and the height is 45,000. You'll find that the error between the geometric horizon and the apparent horizon is less than 0.8%.
Well, there's
Chris,
no such
do you
thing
know
as a geometric
any math?
horizon. It's always and only ever apparent. That's why you argued that the black swan isn't real.
Like your muscles,
Chris,
Chris.
do you know any math?
Carlos,
Do you know any math, Chris, at all?
we can duke it out, Carlos.
Chris, do you know any math at all?
Why would I need to know math when he can't even figure out what he's measuring to?
No. Do you know any math?
Well, obviously,
Chris, if you divide the adjacent side of a right triangle by the hypotenuse, what's the name of that term?
I'll go on mute until somebody else wants to have a real
You only
conversation.
know how to count soybeans.
So you don't know what the adjacent
Carlos,
side
there's
of
a
a
lot of
triangle
kids
divided
who are
by the
lactose intolerant
hypotenuse is.
and have to have soy milk. So you're making fun of all those soy kids out there who know
So you don't know what the
guys,
adjacent
let's
side
not
divided
find
by
it.
the hypotenuse of a triangle is, do you, Chris? How about the opposite side divided by the hypotenuse? What's that term called?
It's called, this is a deflection because I schooled you on that you're measuring to an apparent position and you
how
don't
about
like
the
it.
opposite
So now
over
you're
the
trying to act
adjacent?
smart,
No,
even though you just got
schooled me?
schooled.
You
Schooled.
schooled
You didn't
me?
get Chris, you didn't
Absolutely.
school anybody.
Actually, Chris, what I did was I just crushed your entire argument.